Good day everyone, I am Engineer Mark from MIDAS IT Philippines, and today we will learn about the automation function in MIDAS. And in this webinar, we will only focus on the design of the slab or the design of planar elements like the slabs and the walls. So the design of the frame, including the seismic analysis, will not be covered. So MIDAS Gen automation function is actually a very powerful tool, not just for analysis but also for the design. So let me show you some of the basic application of the automation function here in MIDAS. So as you can see, you can also model, analyze, and design the wind turbine foundation. You can directly model your mat foundation with your superstructure attached to it. So aside from modeling, you can actually do the analysis and design also. For the chimneys, as well as the cellular beams, the silos, and the mat footing, separately modeled and designed. So going back to our presentation, so some software which do automation or which do meshing in their programs, actually you can find some errors or warnings like the loss of loads. So here in MIDAS, you will be avoiding those errors or those mishaps regarding modeling, analysis, and design of your plate elements because of the auto meshing functions. So I know some of us experience those loss of loads which actually affect our overall design of our structure. So for our topic for today, so we will be discussing the analysis and design of the mesh slab and wall in MIDAS Gen, an application of auto mesh function to low-rise apartment building. So for this, we'll start with the basic modeling or structural modeling, the application of loads, the flexural design, and checking of the plate elements, as well as the punching shear check of the slab, serviceability check of slab, and the mesh wall design. So as you can see, these are some of the worldwide application and advanced feature of MIDAS Gen. So for the buildings, we have this, the plant structures, spatial, and the specialty structures. You can also model all of that here in MIDAS Gen. So for the advanced features of MIDAS Gen, you can do the construction stage analysis, post-tension analysis, heat of hydration analysis, as well as the detailed analysis. So for the worldwide application area or the advanced feature, again for the GUI, here is the graphical user interface of MIDAS. So we have these different menus. You also have this work stream where you can find all of the information of your models, the message window and the command line, same with your CAD software, the status bar, table windows, the task pane, all of that you will see actually here in the user interface of MIDAS. So let us start with the architectural plans, initial framing plan, design criteria, and other structural parameters. So for our ground floor plan, so suppose this is the ground floor plan submitted to us by the architect or our client, and this will be the second to fourth floor plan with a typical floor-to-floor height of 3.2 meters, as well as the roof deck. So after consulting the architect as well as the client, after that you will all agree with the typical floor framing plan that you have initially set. So suppose this is the typical floor framing plan that you have already set and approved. So this will be in our modeling. And the design criteria will be this. So the design code that we will be using is ACI. Of course, it is also related to NSCP. The UBC for our seismic, and for the wind, IBC or the ASCE 7-10. So these are some of the compressive strength of our materials. So slabs and walls, 3000 psi. And for the reinforcing bars, these are the consideration. So for the dead loads or the design loads that we will be using, so most of these came from the NSCP, as well as the live loads that we will be going to use in our case study. So although the seismic static load as well as the dynamic load is included here, so we will not be tackling more of that. And of course, for the wind load, we will be using IBC 2012 with the following wind load parameters. So for the design criteria, the loads to be considered in our structural analysis or case study. So for the rooms, we have this dead load and live load, the corridors, as well as the roof deck. And of course, when we model our structure, we initially have to set our initial section. So suppose these are some of the initial sections that we will be going to use here in our case study. And for the slab, it will be 125 millimeter thick, and for our walls, let's say we will be using 250 mm thick of wall. So if you will be importing your AutoCAD DXF file, what you will have to do first is to connect those beams or those columns by creating just like a framing plan using this line. So what I do here is actually I created a layer which I name MIDAS layer, and I connect those points or the column points where I want to put my beams. So we also have to take note that the unit that we will be going to use in our CAD software must be also identical or the same with the MIDAS software. So let us begin our basic modeling. So let me just create a new file. So after creating a new file, I can just first save this. And after saving your file, what we can do next is to define our properties. First, I go to Properties tab, Material Properties, and I can define the strength of my material for concrete. So for this, I can use ASTM-RC. For the main frame, it is grade C 5000. And for my planar elements, I can use grade C 3000. So after defining the material strength, I can also add our initial section. For the solid rectangle, so for columns, I will be using an example of C500 by 700, user defined. And C500 by 600. So as you can see, it will be reflected into the properties dialog box. So for the girders, I can use the 350 by 500. We also have the girders or girder of 350 by 450 for our interior girder. And for our stair beam, let me name this as STB 300 by 400. So after we have done the section definition, we can now define our thickness. So I can add for the slab, let me name it as S125 with a 125 millimeter thick slab. Click on apply, and for the wall, I can name it as W_250. So I can add also the thickness. So after defining the section, what we will do next is to add also the section scale factor or the stiffness scale factor. So for the column, we normally do is to add 0.7. We can also do or add the different stiffness scale factor in our structure. So for the beam, we normally do is to add the 0.35 stiffness scale factor. again, after adding the stiffness scale factor, we will now go to the importing of the CAD DXF file. So first, let me set up the units. So since I have said before that I use the millimeter units into my CAD software, so it should be similar to the MIDAS Gen software. So I can import AutoCAD DXF file. I can browse for the file, and I can import the layer that I have created. Considering the strength of material 5000 psi as well as the section of concrete, let me have a base section of 350 by 500, and let's say I will be doing this into a second floor. So I will be importing the framing plan that I have created to be on the second floor. So I can just create 3200 from 000. So after that, I can now click on OK. So as you can see, the AutoCAD DXF file is now being imported. So what we will have to do next is to assign the different properties. So in order for us to view easily, I can just hide the section, going to the top view. And from the works tree, as I have said before, you can also view the information of your model. Using select single, I can assign the different section. So for this, for the interior girder, I will use G350 by 450 using drag and drop. So for the stair beam, I can also use drag and drop. So after assigning the beams into our model, so what we will do now is to create our column. So how do we create our column? So to create our column, there is an extrude option that you can do in MIDAS. So node to element tab, I will reverse the I to J, or the starting point to end point, and I will just select the C5000 with the section of C500 by 700 with a beta angle of 90 degrees. So I will rotate it into 90 degrees, but we have to make sure that the unit is in mm, so I will just have to set it into meters. So since the floor to floor height is 3.2 meters, so I can just create a negative 3.2. So it will be generated downward. Sorry, I haven't selected the node first. So first I can select all the nodes. So I can use select by plane, XY plane, and I can easily select through the XY plane just like that. And I have to unselect this. So I don't want to have a column in this portion. So using again select single and shift key from your keyboard, so it will now be unselected. So after that, click on apply. So going to the isometric view, you can now see that the columns are being generated. So again, going to the top view, we can also assign the section of the interior column. So how do we assign the section of our interior columns? So same just like before, you can just go to the drag and drop. So first, let me go to the toggle work tree. So I can go back to work tree using select single, selecting those nodes. So first, let me check the selection filter. So I want to select only on the Z. So I will have to again select. So going to the isometric view, it is now selected. So I can now drag and drop the C500 by 600. So let me check. So after the columns and beams are being selected and assigned to its proper location, so we will now first go to the display. So we want to check the assigned section is actually on the proper location. So I can just go to the draw tab, section per thickness color, random color, click on apply, and okay. So same color means same section. So after we have created our column or changed the color of our section, So we can now create our wall. So to simplify this, I can just go to top view, and again, I can now go to the selection filter as none. So we can now create our column using again the extrude option. So extrude, using select single, I can select these elements that I will have to create the wall. So going to line and the element tab, so I don't want to remove the beams. So I want to retain the beams in this framing plan. So for the element type, I will be using plate. And for the grade of our material, so 3000, and I can now select the walls. And again, same height, it is in negative 3.2 projection. So after that, I can now click on apply. Going to the isometric view, the walls are now being created. So after the wall is being created, so what we can do next is to auto mesh this wall using auto meshing function. Again, I can first go to the auto mesh function, selecting the planar element. Using select single, I will have to select these walls. And for the length, so let me use, for example, a length of 0.5 meter. For the thickness, it is 0.25 for the wall, and for the material, it is grade C3000. So I can now apply the auto mesh. So as you can see, we have now meshed our walls. So after meshing the walls, we can now use also the auto mesh function for our slab. So how we can do that? So we can now first select the line elements here. So after selecting the line elements, so what we'll do now is to select those line elements where we will uh, put the slabs. So let me select a point on the XY plane. So here, as you can see, it is now being selected or easily selected. So after being selected, so this is an opening. Actually, this is for the stair. So I don't want to include that into our automation function. So I can now just first unselect using select single, and then shift key unselect this beam. And same just like before, I can now use the 0.125 meter thick of my slab. So as you can see, the slab is now being created. Let me just undisplay the nodes. So there you have it. So easily modeling of the plate elements can be done here in MIDAS Gen. So after creating the slab and wall here in MIDAS, what I will do next is to activate first the other three menus. So the other information or the information of my model will also be seen here in the 3 menu 2. So right click on the tool tab, toolbars, and then check on the 3 menu 2. So after doing that, I can check on the works tree, and on the works tree, so these are the slabs. But slab should be a thin element, not a thick element. So what do I mean by that? So let me go to my presentation. So thick versus thin. The thick option consider the shear deformation and the thin does not. So generally speaking, for the slab, we normally use thin because the shear deformation is negligible compared to the bending deformation. So we will do that here in MIDAS Gen. So we will convert the slab into thin element with, so now we will be having an issue with drilling degree of freedom or without drilling degree of freedom. So if you want to consider also the additional stiffness in your structure perpendicular to your plate, so you can also consider the plate without, I mean with drilling degree of freedom. So the additional stiffness will be considered. But most of the time, if we model the slab, so we normally do the plate without drilling effect or the additional degree of freedom. So there will be no additional stiffness that we will be having into our plate elements. So how do we do that into MIDAS Gen? So I can just select the properties. So we have to understand that especially when we model the slab, it is supposed to be a thin element. So to do that, I can just change the properties into thin element without drilling effect or drilling degree of freedom. So additional stiffness will not be considered into the slabs or the plates, and click modify. So after we have modified the properties of our plate for the slab, so what we will do next is to generate the building or copy the floors. So I can just go to the front view. Again, I'm on the select single option. I can select all of the elements and then going to the structure tab, control data and building generation. So we have a 4-story with roof deck, so I can copy it 3 times with a typical floor to floor height of 3.2 meters. I can add, and now I can apply. So as you can see, the floors are now being copied. So after creating the floors, we also have to define our story for our to consider into our floor. So this will be the ground, the second, the third, the fourth, as well as the roof deck. So going to the story tab, to generate story data. So we have the 3.2, 6.4, and click on OK. So we can also display the story numbers in our structure. So we have the first floor, second, up to the roof. So after we have created the story data, which will be considered for lateral forces, although lateral forces uh, will not be covered here in our case study. So what we will do next is to apply also the boundary condition or the support. So for the support, I can just go to the boundary tab, define support, and I can just select the D all and the R all, which represent the displacement and the rotation. So I want to constrain that into displacement and into rotation. So meaning it is a fixed support. So after doing that, I can now easily select all the bottom nodes again using plane select or the plane and volume select. So going to the XY plane, selecting all the bottom nodes, and I can now click on apply. So let us check if it is properly applied. I can just display. So it is easily applied into the bottom nodes. So of course, after we have created the nodes, we can now define our static load cases. Going to the load tab, static load, and then static load cases. So what I will do, I can add the self-weight using dead load as a type. I can also add the superimposed dead load, the live load. So these loads is the one that we will be going to use in our case study. So for the wind load along X, I can consider wind load X, wind load Y, EQX, considering the earthquake type, and earthquake along Y. But of course, in actual practice, you also have to add some, for example, the additional eccentricity, the negative eccentricity. So you will add other load cases, static load cases. So after adding these basic static load cases, so what I will do next is to convert the self-weight into masses. So this is actually very important, especially when we will be doing seismic analysis. So I want to convert it all only onto XY direction. So if I want to analyze my structure only for the lateral forces, so without considering the vibration of the, for example, in the slab, so I can consider the convert X to Y. I can also check the align beam and align the top of slab for display purposes only. And as you can see, it is now being aligned. So after adding the self-weight or converting the self-weight into mass, I can now also add the self-weight. So to add the self-weight into our structure, I can just use the SW for the self-weight and given a factor of -1 along Z. So I can add for the self-weight and also the loads to masses. So these are some of the important things that we should add, especially when we will be doing a seismic analysis. So I can just simply add the self-weight and the superimposed dead load. So there are other provision, like if you will be considering also the live load, the 25% live load. So you can also do that here in MIDAS Gen. So going to the isometric view, after doing the application of the static load or the definition as well as the self-weight, I can also add the definition for the pressure load type. So for this, it is just a load group that you can actually easily apply to the specific plate elements. So what I can do is to define first a room with the superimposed dead load and considering the live load. So for this, I can add -2.54 based on our design criteria with a live load of -1.9. Clicking on add, and of course the corridors with a live load of -4.8, and the last one will be the roof deck. So for the roof deck, the superimposed dead load is -0.63, and for the live load, let's say -1.9. Clicking on add, and after that we can now apply those gravitational or gravity loads. So to do that, I can just simply activate by identifying. So activate by story, considering the second, third, and fourth floor. So this is a typical floor level. So I can just activate the floor only. After doing that, I can simply apply the floor load or the pressure load into my model. So what I will do next is to apply the pressure load. So clicking on the pressure load and going to the load type, I can use rooms. So for the rooms, it is located in this portion of our plan, and of course in this portion again of our plan. So I can just simply apply those pressure loads. So let us check if it is applied. So as you can see, it will be or it is applied into the portion that we selected. So for the corridors, we can also apply the loadings on the corridors. So going to the top view, so let me just undisplay this pressure load so it will be clear. So selecting the corridor portion of our plan, I can now also apply the corridor load. So selecting corridor, clicking on apply, will now be applied. And the last one will be the roof deck. Going to the isometric view, Activate by identifying I want to activate the roof. So floor only, going again to top view, selecting all of the plates and selecting the load type name as roof deck. I can now apply the loadings. So after applying the lateral or the gravitational load, so let me view all of the structure. Control A or activate all. So after applying the gravitational load, we can now also apply the lateral loads. So for the lateral loads, let's start with the wind load. So we can consider the IBC, and considering a 250 miles per hour, at 250 kph, I can convert it. So I can just divide it by 1.6. For the exposure category, based on our design criteria, it is B. And we can also consider the eccentricity, different eccentricity in our lateral forces. So for if I want to act this wind load along x direction 100%, so I will just make the y direction 0%. So I can now click on apply, interchanging this into wy. I also have to interchange the scale factor to 0 to 1. So after adding the wind loads, I can also add the seismic loads. So same with the wind loads. So for the soil profile type, based on our design criteria, it is SD, seismic zone 4, closest distance is 5. We can also calculate the period by code. So this one is, the first one is for steel, the second is for concrete, and the third is for other structure. So having a ductility coefficient of 8.5, and same with the wind load scale factor, I want this to add into x direction. So I will just have to scale it at 1, 0. So I can now click on apply, interchanging this again, 0 to 1. So I can now click on OK. So after that, you can also view the different story force, story shear, and you can also see how does the MIDAS work in calculating these forces. So after applying those loads into our structure, we can now also add the load combination. So I can just go to the results tab, load combination, and for my analysis, I can just go first with the general tab, auto generation, considering concrete. So will not be doing any response spectrum scaling, and I can now click on OK. So the load combination based on the ACI code will now be considered. So for the concrete design, I can also use the auto generation, same with the process that we have done before. So I can now click on OK also. So after adding the load combinations into our analysis, we can now perform the analysis. So perform analysis. So in 5.63 seconds, the analysis has been completed. So with this, I can now view the different results. So for example, we will be focusing more on the plate. So I can just go to the plate forces moment. So for the plate forces moment, you can select any type of load cases or load combination you want to view, considering the moment on X direction or different components that you want to reflect. And after that, I can view also the legend. So I can now click on apply. So as you can see, the moment based on this load combination, this actually the load combination that I use, GL, or the load combination 2, which is actually the 1.2 dead load and 1.6 live load. So you can have these different forces or moment in your plate elements. So what I will do next is to see the forces or the actual moments in the plate elements. So let me isolate a portion of our structure. So let's just isolate second floor. Let us analyze the second floor. So I can consider the plus below. So meaning the floor or the element connected for the second floor will be viewed active. So we are on the second floor. So after doing that, we can also do, or we can also view the cutting plane diagram, or the moment diagram on the slab. So I can just click on the cutting diagram. After clicking on the cutting diagram, I can just select a 2 point where I want to display the loadings. So 2 points. So cutting line 1 is now being created. So after creating the cutting line, I can now click on apply again. So as you can see, this is the cutting plane diagram, or the moment that is being produced in the XY, or in the X direction. So considering moment along XX. So I can view it also in graphs. So as you can see, this is the graph being created based on the cutting plane diagram, and you can also save this graph as image. So that is the stresses or the moment considering the load combination that we have selected. So after viewing the cutting plane diagram, we can now proceed with the design. So going to the design tab, ACI. For the design code, we will be considering ACI 318-14. And for the modify concrete material, so grade C5000. So if we will be designing our frame element, we can select, for example, for the main rebar, I can use grade 60, and I can use grade 40, grade 40 for the sub rebar. So after doing that, I can just modify. So for the slab, so I can use ASTM-RC, and for the main rebar and sub rebar, I can use grade 40 as well. So after adding the concrete strength, or the rebar strength for the design, so we can now select the slab wall load combination. So for the slab wall load combination, you can select what type of load you will consider into your design. So for this, I can just select any of the load combination for strength, serviceability, and deflection for the slab or mat, as well as the wall element. So after considering those load combination, so what I will do next is to provide the design criteria for rebar. So for the design criteria for rebar, I will just uncheck the basic rebar for slab or mat. So that means that I want the software to automatically calculate the required diameter, or the spacing, and the diameter. So first, I can set the initial diameter for the slab as 12, considering the different diameters. And for the wall design, so for vertical, I can use only 12, and for the horizontal, MIDAS has an option to consider a 10 mm and a 12 mm diameter rebar. So I can now click on OK. So after doing that, we have assigned the different section or the different rebar properties. we can now go to the uh, slab flexural design. So we can now perform the flexural design. But first, let us know how does MIDAS compute for the slab flexural design. So MIDAS actually uses a wood armor moment. So what is this wood armor moment? So wood armor moment method is actually a method in a structural analysis based on a finite element or, a, or an FEA. It is used to design the reinforcement for concrete slabs. These methods provide the simple equation to design a concrete slab based on the output from a finite element analysis software. So in our presentation, so for the flexural design of our slab, so these are the, from the analysis result, we can get the different moments along X, Y, and along XY plane. So this is the common formula which is the wood armor moment is derived from. So for the bottom rebar and the top rebar, the software will use this formula to calculate the required reinforcement in our structure. So let us now perform the flexural design. So for the flexural design, again, I can go to the mesh design, flexural design, and I can select the all load combination or the all combination considering the both direction of the reinforcement. Of course, you can also view the reinforcement or the required reinforcement on the top or bottom. So for this, I can just use the both, or I want to view the both top and bottom rebars, and I can now display the rebar, and I can now apply the design. So of course, having a finer mesh means having a, what you call this, a more exact result. But of course, having a fine mesh will also, you will also have to consider that post processing or the analysis time that the computer will use, since many elements means a larger time of analysis. So what is actually also good here in MIDAS that I forgot to tell you is you can also perform the analysis and design, especially if you are doing a high-rise structure and you have modeled your plate elements. So the analysis and design will take a very, very long time. So what you can do here is to isolate, for example, a floor level into your structure, and you can also design just what I did here. I can just design the second floor only into our structure. So after doing the flexural design, we can now see the reinforcement. So these the colors representing the reinforcement needed. So I can also view the values. I forgot to add the values. So there. So the values. So let me select a portion of a slab that I want to consider. So using select single, I want to isolate this portion only. I want to view this portion only of my slab. So I can just activate those. And I can now view the results. So as you can see, the different spacing as well as the rebar diameter is being presented here in MIDAS. So if I update this rebar, so these are the rebars that is being used into the model. So I can just click on the properties. If I want to edit the rebar properties into our design, you can also add the rebar properties. Change the spacing or the diameter. You can also do that here in MIDAS Gen for your checking. So after doing that, let's say I want to change a portion of this slab. So we have a portion of slab which has 200 millimeter spacing. So this portion actually requires us to have a spacing of 200 mm for the bottom direction along direction 2. So direction 2 is actually along the y direction. So what if I update this rebar? So I want the rebars to be uniformly distributed. So I can just first select the rebar. It is again highlighted, or the plate with the rebar of P12 by 200. So I want to assign the P12 at 300. So I can just simply drag and drop and it will now be assigned to that specific element. So after doing that, let us check the result. So we can check the result if the changes that I have made will pass or fail. So since it is required that this portion of the plate element is, we have to use the 200 mm spacing. So I think the there will be an issue if we have to check this portion of the plate. So this issue I mean is actually a failed on the resistance ratio. So let us check for the flexural checking. So again, both direction, both portion of the slab, the top and bottom, and I can just view the direction 1. So I want to check the resistance ratio. So as you can see, uh, it has a resistance ratio of 1.0, but let us check with the actual design results. So we can check on the design results. So let us check if there is a no good to our plates. So MIDAS Gen will show you the different information after we have checked. So as you can see here in MIDAS, it will show you not just the numbers, if it is as well as if it is failed or not good, or it is okay. So you can actually see how does the software work. So you have these different properties, the load combination that is being considered, as well as the information of the model and the actual computation. You can also verify if you want, considering those results. So as you can see, you can verify the results. So it is not a black box that you can just see the result that it is okay or not okay. You can verify it manually. So as you can see, it is all good. So meaning the 300 mm spacing of the 12 millimeter rebar is also good in that portion of our slab. So after doing the slab checking for the flexure, we can now also do the slab shear check. So the slab shear check, so let us go first with the presentation. So for the presentation, how does MIDAS calculate for the slab shear check? So MIDAS Gen uses this formula. So it is actually also based from our code. So we have this formula, Vn is equal to Vc plus Vs. So the nominal strength is equal to the concrete strength of the shear concrete, the shear in concrete, as well as the shear strength of the rebar. So for the shear strength of the reinforcement, it is calculated by this way. So in MIDAS Gen, required rebar area is calculated by Vs is equal to Vn minus Vc. So it just interchange the formula. So the shear rebar spacing limit and minimum shear rebar area are not applied. So for the required strength, shear strength Vu, this is how the software actually calculates for the Vu. And for the slab shear checking, though, so punching shear check by code, this is the normal procedure that we actually do. The maximum shear strength by concrete based on the code provided. So in MIDAS Gen, the above limitation is applied when the slab thickness is larger than 200. So for finite element analysis, we also have this method in how the software calculate the punching shear using the finite element analysis. There are two methods, so case 1 and case 2. So we also have these two methods, the average by elements and the method 2 is average by side using the finite element analysis for the shear check of the slab. So to do that, here in MIDAS Gen, so going back to the MIDAS Gen file or model, so I can now see the slab shear checking. So I can consider the code. So after considering the code, I can now click on apply. So as you can see, the result is now being generated. So we can now see the punching shear check into our slab. So we want to view the detailed formula or the detailed calculation. So we have to verify how does the software work. So we can also do that using the design results. So we can also view the design result in MIDAS Gen. So same with the flexural design. We can also do, or we can also see how does the software calculates for the shear check or the punching shear check. So after doing that, after we have done the slab shear checking, so the final method is the serviceability check. So again, how does MIDAS compute for the slab serviceability check? So let me go on again with the presentation. So for the serviceability check of the slab, these are the formula that is being considered by the software. So calculating of course the stresses in concrete as well as the stresses in the steel first for the uncracked section. So for the considering the ACI code, so it also follows the code using this formula. So to do this in MIDAS Gen, so same process with the flexure and shear check. So I can just first set the slab serviceability parameters. So let me say I will be just using all of these into L over 360, the deflection control. But you can also use a user defined. For simplicity, I can just use L over 360. So selection type as all. So I can now select and apply and it into the model. So after applying the serviceability check into our slab, so what I will do now is to perform the serviceability checking. So perform the serviceability check for the cracked section, uncracked section. So you can now view the serviceability ratio. So to check the design result, we can also view the detailed calculation. How does MIDAS calculate for the serviceability? So the information of the model as well as the calculation is being reflected here in MIDAS. So you can also verify those. So what if we will be considering a long-term deflection, let's say 5 years or more? So the time C will include the creep and shrinkage. But if you want a creep only, you can also do the creep. So time C, considering the creep and shrinkage. Again, I can now view the result as well as the detailed calculation. So as you can see, these are the results gathered from considering the long-term deflection in MIDAS. So after doing the slab shear checking, the last is also the mesh wall design. So in mesh wall design, so first let us view how does MIDAS again compute for the mesh wall design. So in MIDAS, so wall design forces and tension reinforcement are obtained in an element subject to in-plane orthogonal stresses. So the in-plane orthogonal stresses being calculated, and then it will be used to determine the reinforcement. So these are the formula that is being used, and the reference will be the limit analysis and concrete plasticity. So that is how MIDAS Gen consider using the wall design. So for the minimum reinforcement for vertical and horizontal rebar, we have we can consider the code, the ECA 318, and considering the different parameters on that, like the 0.0012 minimum rebar reinforcement, you can also set a separate value for your shear wall or your wall design. So going to do that into our model, so I can now also perform the wall design. So considering, for example, horizontal reinforcement, or let's say vertical reinforcement, so I can view the rebar. So I can now apply. So I will just check the reinforcement. So here it requires we have we should have a 12 millimeter diameter at 200 spacing of our rebar in vertical direction. So how about horizontal direction? So it needs a 10 mm at 100 spacing. So we can also do the update rebar. So same just like in slab, we can also update the rebar. And aside from updating the rebar, you can also change the vertical and horizontal rebar diameter as well as the spacing. So that is how we calculate the stresses, we analyze as well as design plate element in MIDAS Gen. So before I end this presentation, let me show you the latest version that is actually the release note of the latest MIDAS Gen 2020. So it is actually released earlier this week. So it considered the different for the MIDAS Gen. So it improves some of the vertical member design, which is the column, and some considering the different codes. And also it has added some of the features in the MIDAS Design Plus. So what are these? So improvement of vertical member design. So we can now add the design by constant P. So support seismic design by axial force P constant method. And apply axial force constant method to all or individual columns, wall or braces. So the axial force will be constant. So for the different codes, improvement. So for the time history analysis, it also improved. And the analysis speed is also improved. So this is the latest version or the latest release of the MIDAS Gen. So you can have this latest version if you avail this MIDAS Gen software. And of course, last is the MIDAS Design Plus. So in MIDAS Design Plus, it also added the AISC 341-16 design tool. So calculation of unbraced length of beam bracing. It also has the calculation of axial strength of point bracing, the calculation of axial strength of point bracing, the design of link stiffener for I section, considering the AISC, and of course the design of link stiffener for I section also for AISC 341-16, the calculation of beam strength with K-brace, and the anchor bolt module. So the anchor bolt module, the spacing, the tensile, the shear strength, and the combined ratio check for post-installed and cast-in-place anchor bolt is now being considered, considering the ACI 318 code and NSR-10. So procedure for the anchor bolt design is, so as you can see, you can also perform the anchor bolt design and the detailed calculation as well. So again, I am Engineer Mark Espino, Technical Support Engineer from MIDAS IT Philippines. And if you have any other issues or concern, don't hesitate to contact us at philippines@midasit.com or phinquiry@midasit.com. So that will be all. So thank you.